We've already learned the idea of the mole. Like a dozen is 12, to a chemist, 1 mole represents 6.022 times 10 to the 23 particles. Doesn't matter what we're counting, no matter what we're counting, whether it's atoms or molecules or ions or what are called formula units, 1 mole is always equal to 6.022 times 10 to the 23 particles. This number is known as Avogadro's number. If we look at this table here, we can work through some examples. If I have 1 mole of neon, what I have is 6.022 times 10 to the 23 atoms of neon. At the same time, if I have 1 mole of CO2, I have that many CO2. But because CO2 is a molecule, the type of particle is a molecule, so I will call it a molecule. But I have this many, 6.022 times 10 to the 23 molecules of CO2. If I have an ionic compound, 1 mole of sodium chloride, I still have the same quantity of that sodium chloride, 6.022 times 10 to the 23. But because sodium chloride is ionic and it doesn't exist as molecules, the term that we use to describe it is formula units. Formula units is the equivalent of molecules for ionic compounds. So as we can see, no matter what we're counting, if we have a mole of it, we have 6.022 times 10 to the 23 of it. Now, we're not always going to have a mole, so we need to know what to do when we have different amounts. So for example, if I have half a mole of neon instead of a full mole, I'm going to have half of Avogadro's number, or 6.022 times 10 to the 23. And right now I'm not too worried about calculating it, because what we're doing here is we're just deriving the formula that we're going to use. So I have 0.5 times 6.022 times 10 to the 23 atoms. At the same time, if I have 2 moles of CO2, that means that I have 2 times Avogadro's number of molecules. So to find out that quantity, if I want the exact value, I'm going to multiply 2 by Avogadro's number. And because it's CO2, a molecular compound, it's molecules. And if I have 0.25 of a mole, that means that to find the number of particles that I'm dealing with, I have basically a quarter of Avogadro's number, which is 6.022 times 10 to the 23. So I multiply 0.25 by Avogadro's number. And again, because this is an ionic compound, when I'm counting it, it's going to be formula units. So what we've just done is we've derived a relationship between the number of particles and the number of moles that we have in a sample. If you want to know how many particles you have, you need to take the number of moles that you have and multiply by Avogadro's number. And so the formula looks like this. Large N, which represents the number of particles, is equal to the number of moles that we have times Avogadro's number. So this, big N, represents the number of particles. And this can be atoms, it can be molecules, or it can be formula units, depending on what we're counting. Small n is the variable that we use to represent the moles that we have. And moles is just short for molecules. It's a way of counting. And then this symbol here is representative of Avogadro's number, which is 6.022 times 10 to the 23. And this is the number of particles per mole. Now, we need to be able to use this formula very, very well. And so if you need to use a triangle in order to help you to rearrange this formula to be accurate all the time, then please do so. Okay? To set up such a triangle, what you need to do is you need to put the large N at the top, and then it's going to be moles times Avogadro's number. And the way that these kinds of triangles work, they help you to rearrange the formula. So whatever you're looking for example, if I'm looking for N, I cover that up, and it's moles times Avogadro's number, which is what we've been doing so far. But in another example, you'll see we want to find moles. So if I cover this up, then you'll see that to find moles, it's going to be the number of particles divided by Avogadro's number. Let's do some examples. Okay, in this first example, we want to calculate the number of atoms present in a sample that has 2.5 moles of lead. Okay, so we can see we need to work with atoms because we have Pb. I'll just write our little triangle at the top here. So our triangle is big N, little n, and Avogadro's number. So I'm given my little n, or my moles, and I'm trying to find my big N. So my large N, or my number of particles, number of atoms, is equal to the number of moles that I have times Avogadro's number. So we've got 2.50 moles times Avogadro's number, which is 6.022 times 10 to the 23. And when I do that math in my calculator, I get 1.51 times 10 to the 24. Okay, so you'll notice that I'm reporting my answer to the correct number of significant digits. 2.50 has 3. Avogadro's number has 4, so I need to report my answer to the fewest number of significant digits. And because I'm counting lead atoms, my units for my large N are atoms in this case. Here we have another example, and this time we're counting the number of molecules because we're dealing with NH3. And this time we have a very small number of moles, a fraction of 1 mole. And so to calculate that, it's the same formula. And I'm taking 0.225 times Avogadro's number, which is 6.022 times 10 to the 23. This number again has 3 significant digits, so my final answer should be reported to 3 significant digits at 1.35 times 10 to the 23, and my units this time are molecules. In my last example, I'm dealing with an ionic compound, and so I want to know the number of formula units. So my formula is calcium hydroxide. I know it's an ionic compound because it has a metal in it. Again, I'm using the same formula. This time, I only have 2 significant digits. So when I report my answer, I need to report it to 2 significant digits and round it properly to 4.5 times 10 to the 23 formula units. Okay, so that's one way that you'll be using this formula. You'll be given the moles and you'll be asked to find the number of particles. The second way you'll be asked to use the formula is by finding the moles from the number of particles. So again, if we refer to our triangle, big N on the top, little n, and Avogadro's number. This time, we're given the number of atoms in the sample. So this is big N. So if you're given atoms or molecules or formula units, that's your large N. And we want to determine the number of moles, which is our lowercase n. So N is equal to big N over Avogadro's number divided by Avogadro's number. We have 3.02 times 10 to the 23 divided by 6.022 times 10 to the 23. you can see with this number, we should be expecting somewhere around 0.5. So it's important for you to think a little bit about the numbers you're working with so that you can estimate, so that when you use your calculator, you do have an idea of whether or not you've entered it properly. Okay. So this number here, we get 0.501 when we round it, and the units for little n are mole, or MOL. In example 2, we're asked to find the number of moles in a sample containing a certain number of formula units. So it's the same when you're given the formula units, that is your big N. So to find the moles here, we're going to take that big N, or the formula units, and we're going to divide by Avogadro's number. Okay? And you're going to want to make sure that you don't just write this down, but you practice entering this into your calculator, because using scientific notation in your calculator is something that requires practice in order to be accurate every single time. This time, we only have 2 significant digits, so when I report my answer, I'm going to round it to 2 significant digits at 1.4 times 10 to the negative 3 moles. Okay? You may also record your answer not in scientific notation, but using a decimal place. That is fine, okay, as long as you have the right number of significant digits. Okay, and you should try this next one. So take a minute and pause the video and try this next example. And what you should get is 9.0 moles. You've got 2 significant digits, and you should get 9 moles. And this one is a bit tricky with the rounding because you have 8.967. And so when you round the 6, it bumps the 9 up and you end up getting approximately 9, but you need to put it to 2 significant digits. So that is 9.0. Okay, this concludes the lesson on working between moles and number of particles.